In this module of Process Dynamics and Control, we'll compare a simplified energy balance that includes convective heat transfer to the actual empirical model with the Temperature Control Lab unit. You can see in front of me the simplified energy balance, which includes the mass and heat capacity of the Temperature Control Lab, as well as the differential temperature over time. And on the right hand side of the equation is equal to convective heat transfer and generation from the heater. We'll simulate this as the heater is adjusted to 50% over 5 minutes. You can see the perspective values of the constants below. We'll focus more on the code and what's going on in this module. First, let's discuss some general principles on what will happen in our step response code. Here we'll first CLC clear all and close all as we always do, and we'll set the current working directory to the folder that the live script is in. We do this so that if you look at our current folder, I have each lesson organized into its own folder. And this allows us to save files where they'll actually be, or where we're working with them, I should say, rather than wherever the current working directory is on your operating system. We'll use try-catch blocks to load saved data if it exists, and otherwise simulate the Temperature Control Lab unit. First, we'll create a file name for our saved data. I chose TCLab _data.csv. Then we'll use the try block to read the matrix if it exists, and then separate the data into columns. If their data doesn't exist, then we'll move on to the catch portion, as we'll catch an error. Within the catch portion, we'll first run the Temperature Control Lab and collect data, and then save that data in a matrix. If that doesn't work, we'll turn the lab off and close the lab so that the lab isn't left on. We'll first call the lab as lab equals TCLab. Then we'll create arrays for our simulation with T1 and TM as arrays with zeros. We'll turn the TCLab to 50% and start our timer. Then we'll loop through the values, filling in the time and the temperature measurement, as well as graphing the data. Then we'll pause for 1 second and repeat the loop. As you might be able to tell, because we're pausing for 1 full second, each measurement will be more than 1 second apart, as it also includes the time to record the measurements and plot. That should be fine though, because we're recording the time in conjunction with that, the temperature measurement. So we should be able to see a characteristic line, so then be able to compare that to our simulation. Finally, we'll use A equals and then create a matrix of time and temperature, and the right matrix function to save our data as a file name. Let's go ahead and let's look at how this runs. Alright, here we have our results. You'll see first the graph that was created, and as well the matrix that was created and saved. The first column being the time, the second column being the temperature in Celsius. If you have any questions about running the TCLab or the path, be sure to check out my video on how to add the path to the Temperature Control Lab module. Move on from here to our simulation and plot real quick. To make our simulation, we're going to use ODE 45 as we've done before. First, we're going to create T, which is a length space from 0 to 300, which is 301 entries. Next, we're going to put our results in a matrix that includes TT for time, just time of the results, and then temperature In ODE 45, we're going to give it 3 arguments. The first is going to be our anonymous function with convection sim as the function we're integrating. That will take both time and temperature. We'll then give it our time array and an initial temperature of 23. If we look up above, we can see that 23 is not a bad estimate for what ambient temperature is. If we go down to that function real quick, we're going to look at convection sim. We'll see that time doesn't really play an effect to it, but temperature does. If we have all the constants there, U, which is the heat transfer coefficient, TA, ambient temperature, A for area, M for mass, Cp for heat capacity, alpha for the conversion of heater power to wattage output, and Q for our percent power. If we were to actually have that as an argument, we would simply add a Q and then comment out this line. Like so. But we're just going to leave it hard-coded as 50 for this assignment. And then we'll return dt, which is that energy balance as shown before, with everything but the differential off to the right-hand side. So you can see we have our convection term, we have our generation term, and then everything divided by m times Cp. We now go up, we'll look at how we do that. We have those in the ODE 45, we separate the results. Finally, what we do is we plot both our data with the red dots and then our simulated measurement with a line. We'll go ahead and we'll look at that plot now. Great, so here's our plot. Let me just scroll in just a bit more. Let's just think of a few observations. Obviously, they both start right about exactly in line, which is great. We have our measured data slightly lower than our simulated data. And that makes sense if we remember our simulated data only takes into account convection. There's other modes of heat transfer such as conduction and radiation, for example, that would also account for heat transfer. And so our model performs decently well. We're within 5 degrees, but it's not perfect. So as we go on, we'll discuss better and better ways for our model. If you have any questions, be sure to leave them below, and thanks for watching.